Popular songs tell us love is forever. Popular movies have titles like Tomorrow is Forever. And these are fine romantic notions, but there's only one thing I know of that truly lasts so long that relative to our civilizations, it might as well be considered forever. Nuclear waste. Now, there was a time when nuclear energy optimism was so high that pundits predicted clean energy too cheap to meter. And then came the nuclear accidents and, of course, the endless problem that has never been solved: what to do with all the dangerous and deadly wastes. Radioactive materials, which contain unstable atomic nuclei, are unlike any other kind of waste in our human experience. And for most of human existence, apart from our exposure to the radiation of the sun and other cosmic rays, we had no encounter with radioactive materials and their dangers, and no idea that they even existed. In the past, they were usually found only deep underground, associated with the heaviest metals, polonium and thorium and uranium. Naturally unstable, their problem is that, in essence, they are always dangerous to living cells, no matter what form they are in. And that's because the harm they cause is not contingent on their chemistry. It's related to the products of their incessant decay. The gamma rays, the X-rays, the neutrons, the alpha particles, and the beta particles that they throw at you as they decompose on a nuclear level. When a living organism is exposed to the radiation they emit, cells are damaged and die, and chromosomes are altered, creating mutations and cancer. There's no way to stop them from being radioactive. One simply has to stay away from them or shield oneself from their radiation and wait, often for periods of times in the hundreds of thousands of years. Sure, there are ways to stay protected from them if you isolate the source. After all, they were relatively safe for thousands and thousands and thousands of years when they were in their natural form underground, before we started mining and refining them. Now the danger is when they get into the air and the water and the soil as waste. In module ZWRT, when we looked at the biogeochemical cycles of the Earth, the carbon cycle, the nitrogen cycle, the phosphorus cycle, and the water cycle, among others, we saw some pretty impressively long recycling times. Nitrogen can cycle between the atmosphere and plants and animals in a few weeks, and carbon fixed in soils and living organisms can cycle in hundreds of years, but the so-called slow carbon cycle, movement of carbon between rock, soil, and ocean and atmosphere, that can take between 100 and 200 million years, while phosphorus can be even slower. But the thing about these cycles, long or short, is that for the most part the elements and molecules themselves are usually very usefully assimilated into the life cycle at any stage. They're not usually dangerous, and it isn't that hard to get the rates and the forms right. Except when there's too much of the oxides of carbon and nitrogen, for example, overwhelming the natural recycling process and contributing to global warming at a rate faster than they can be removed, or when carbon is in the form of larger chains or ring-shaped biologically active hydrocarbons, and other elements are in the form of biologically active compounds whose decomposition is taking too long and whose intermediate compounds can meanwhile cause cancer or birth defects. Dealing with chemical waste, as we talk about in module TWYRT, isn't really a long-term concern. With a little investment in applied science, we can turn bads into goods. We got this. But when it comes to nuclear wastes, wow. The Nuclear Regulatory Commission tells us that, quote, radioactive isotopes eventually decay or disintegrate to harmless materials. So that's the good news. But they continue, some isotopes decay in hours or even minutes, but others decay very, very slowly. Strontium-90 and cesium-137 have half-lives of about 30 years. Half the radioactivity will decay in 30 years. Plutonium-239 has a half-life of 24,000 years. To determine how long radioactive waste will remain hazardous, we have to better appreciate the concept of half-life. I don't mean the video game where radiation spawns giant ant lions and you can eventually harness them to be your allies in your fight against the alien Combine who are draining the oceans for minerals and replacing the atmosphere with noxious murky gases. Yes, video games like Half-Life and Fallout actually deal with the waste problem, and they deal with it in entertaining ways, but they give you a misleading picture of how the world will look after a nuclear waste disaster. In the case of radioactive waste in the real world, half-life refers to the time taken for the radioactivity of a specific isotope to fall to half its original value. In other words, if you get radioactive bone-seeking calcium-replacing strontium-90 in your milk, or radioactive water-soluble potassium-replacing cesium-137 in your blood, which happened after the Chernobyl disaster in 1986 and the Fukushima disaster in 2011, you aren't going to be safe 30 years later. The half-life of 30 years means that, as the wiki article states, quote, as of 2016, the Chernobyl cesium-137 has decayed by half, but can have been locally concentrated by much larger factors, end quote. It can take many, many, many half-lives to eliminate the dangerous radiation. It's like, imagine a colony of stinging fire ants that you can reduce in size by half every 30 years. It can take generations to eliminate them all, and if you're the unlucky person who gets stung by that one remaining last fire ant, woe be unto you. Radioactive waste is like that. In this module, we'll explore the nuclear waste problem in full and ask ourselves the question, what should we do with the radioactive waste we have? And should we be recycling radioactive wastes? Many countries are doing just that, recycling radioactive waste to cut on the need to mine new uranium. But the problem with recycling uranium is that it tends to turn it into even more highly radioactive and dangerous plutonium. And plutonium has a half-life of 24,000 years, meaning that half of it will have decayed to something else after 25,000 years, but the other half will still be deadly and radioactive. So it can take hundreds of thousands of years for all of it to turn into something safe, and that's longer than modern humans have been on the planet. Let's explore the ins and outs of nuclear waste, and then let you decide if using radioactive rocks to boil water to make steam to run a turbine is really the best way to turn waste to energy. My feeling is it's not, but you may write a glowing report about how we can deal with nuclear waste. Let's see where you stand when the radioactive dust settles.